So, okay, now we can start. So let me just introduce once again about the Anubhav. So actually, today we have Anubhav Chaturvedi, and he did his PhD at ICTQT with Professor Marcin Pawlowski. Later, he joined as an assistant professor at the University of Dansk University of Technology. And today, this is the part two of his lectures on SDP, using SDP to characterize quantum correlations. So please, I'm asking everyone to interact with him in between talk. You can stop him at any time, I think, and ask us questions. Yes, Anubhav, please.
Um, Thank you, Meet, and thanks to Meet and Sunda for inviting me to talk about one of my favorite topics. As Meet said, I would love to address any of the questions that come on the way, and please feel free to stop me. Um, I'm going to recall some of the things from the previous lecture, so I'll go a bit faster here, but please stop me. Um, in the previous lecture, in the second part of the previous lecture, we started um, uh, exploring the application of semi-definite programming to characterization of non-local correlations, um, and specifically non-local correlations that are on offer by nature, which we believe to be is quantum. So basically, quantum non-local correlations. We know that the set of quantum non-local correlations is a convex set, and and what we are really interested in is the answer to a question, which is the membership question. So given no signaling non-local probability distribution coming related to a Bell scenario or a Bell experiment, we were we were interested in the question whether this probability distribution has a quantum realization, which just basically means if there exists some state belonging to any Hilbert space shared between Allison, Bob, and some measurements that realize the probability distribution. Um, this problem of finding whether a point is quantum or not is closely related to another problem that we'll be focusing on today, is to find the maximum violation of a Bell inequality. Um, a Bell inequality in general is a linear functional of probabilities. And for some part of this lecture, we'll be interested in a particular Bell inequality, also known as the CSSH Bell inequality. Here, the CSSH Bell inequality is written in its CGLMP form, or we also call it the CH Bell inequality. Specific and see the CH Bell inequality is very good when you look at detection efficiencies. Um, it has operational meaning there. Um, and the nice part about this notation is it's the minimal notation. Okay, so we will focus on this aspect or this problem, which is in turn equivalent to a membership problem, to the membership problem of whether a probability distribution is quantum or not. So a Bell inequality is made up of tracial terms. Now, here's the thing to notice that that each spatial term has a product of three semi-definite operators of the first racial term, and the other two also have the product of two semi-definite operators that we need to look for in a quantum realization. So this is not a linear functional of the semi-definite operators that are to be searched over. So this is the issue. Um, And finally, you can see that there is no bound on the dimension of the Hilbert space. So even this problem is as hard as the membership problem. Okay. So it's really difficult to characterize the set of quantum correlations
So
in
Anubhav,
Bell experiments. Yes.
Oh, no, I have a query. So, is it hard because that the state of quantum correlation is not bounded, or is it because of that things?
Uh,
Is it something connected to that?
it is also related to that, but just from a first principles perspective, there is no Hilbert space bound on Hilbert space dimension. So if you go ahead and do a simple parameterization of everything, which I do not recommend, I'll show what how the parameterization should be done. If you do that, then the Hilbert space dimension, no bound on the Hilbert space dimension, is the first reason why this is difficult. Um, and the second reason is that it does not really form a numerically solvable SDP problem directly because of the tracial terms having products of semi-definite operators. So they are not linear on the semi-definite operator. So it does not give way to the primal form of nice SDP problems. These are the two reasons that know by confirmation, but it's also related to whether the convex set is bounded or not. These
Okay.
series of reasons. Is it okay?
Yes, yes. Thank you.
Okay, so as I promised, the best way to internally parameterize. So you do not care about what is the best in quantum theory, but you just given the Hilbert space dimension, the best way to numerically approach this problem, again to get lower bound. So this does not say that the maximum violation is this much, but it puts a lower bound on the maximum violation and also gives a realization is the seesaw method. So in the seesaw method, basically you take your tracial terms which had a product of three operators and fix two of the three operators in one round and search over one of the operators. Now the problem becomes really nicely solvable, satisfying for finite Bell scenarios, satisfying strong duality condition also and also the numerical feasibility condition. And each step is guaranteed to return the optimal. Well, depending on the context. For and in the next step of this iteration, we take the optimal that we have obtained from the previous step and search over the other semi-definite variable and take the optimal and continue to the next step. This is the seesaw method. If I get time, I will show you how it's implemented. So a code is just a mathematical description of this. So, but here we have a given dimension, given finite dimension, and there is tensor product structure in finite dimension quantum theory, which is taught in our courses. But I will recall something interesting that from an operational perspective, there is no need for the tensor product structure to describe spatial separations. We can instead describe them simply by commutation relation. So in one picture, there is an Hilbert space which is broken down into tensor product Hilbert space to enforce a no signaling relations on the effective states. And in the other description, there is no such breaking down of Hilbert spaces. There are these additional commutation relations. The second viewpoint comes from a viewpoint of a consideration of a broader notion of um, uh, classicality known as Cohen-Specker contextuality. So this is the building block to NPA. So NPA like hierarchy is also directly applied to coaching specker, uh, bounding coaching specker contextually. So mm, I will now tell you about NPA hierarchy. So NPA hierarchy is an instance of non-commutative polynomial. Is NPA hierarchy is an instance of a non-commutative polynomial optimization problem. uh, where we have a bunch of a bunch of polynomials of of operators which might not commute among themselves. Okay, the central mathematical theorem that underlies uh, method these method is that of the moment matrix is relates to the moment matrix. Okay, so in Bell scenarios, or with even without referring to Bell scenario, in general we will define a moment matrix tau ij, which is specified by a list of operators oi, and those could be any linear operators. Then we know that if tau ij constructed um, in such a way that the ij entries are specified by the trace of some density operator rho with oi and oj dagger is always positive semi-definite. Okay, so we have a theorem which states that if you have a positive semi-definite operator, say a density matrix, and if you take the moment matrix hinged on that density operator with respect to any set of linear operators, then such a moment matrix will be positive semi-definite. This is the one tool that enables such hierarchies, such this theorem, and it's very easy to prove because for pure states you can see that such a matrix forms a gram matrix of uh, the pure state with respect to these operators, and the gram matrix is positive semi-definite. So you can generalize this for mixed states then. Okay, so let
And
us
is there any constraint on this operator, linear operator
none
O?
whatsoever. That's the nice part. None whatsoever. Okay. So we must choose the list of linear operators so that it allows me to solve my problem. So the next question comes, what could be such a list of operators? For Bell scenarios, the list of operators, the first list of operators that we'll consider is identity. And now this is just a symbol. A00 tensored identity and A10 tensored identity is symbol because there is not actually any tensor relation here. I just write it as in this fashion. But in general, there is no tensor product here. So I should have removed it, but this is for specification. Okay, so this is one good list of operators, but they could be unitary, they could be Krauss operators, whatever. In general, such a matrix will be always positive semi-definite. It's okay if we consider the yes,
I'm asking if can OI can be a Hermitian operator?
yes, yes, linear operators, any matrix.
So then your moment matrix tau ij need not be positive, right?
Um, no, it will be always be positive for any linear operator because the terms are OI, OJ dagger. So you know that to PI, PJ dagger, PI dagger, PI dagger, PI is always positive semi-definite for all linear operators.
So suppose rho is 1, rho is ket1 bra 1, okay,
Yes,
and OI is sigma z.
yes.
And can't we choose some OJ dagger such that it would be negative? Because sigma j, its eigenvalues are eigenvectors are corresponding minus eigenvectors is 1, 1. So if I choose rho is equal to 1, 1, and if I choose OY as a sigma j due to the hermiticity and the negative eigenvalue, and can't I choose OJ? Let's OJ dagger is identity.
Okay.
Then it would be negative, right?
The moment matrix should be negative.
Yes, yes, because if I choose OI is equal to sigma j, okay, let's choose OI is equal to sigma j, the j
Can
Pauli operator.
we this is a good question, but I really think so that this will be positive semi-definite, and we can check this after we are done with the if you're okay. But in general, I'm sure I can look up the reference in of the proof in 2 minutes because it's one of Valerius Karani's articles, and we can find find them. But in your case, it's Hermitian, so I'm 110% sure. But it should be hinged on a positive semi-definite operator. So do you got my statement that this is a positive semi-definite operator?
Yeah, let's rho is a 1 1, Kate 1 bra 1.
Yeah,
Okay.
yeah.
And let's
So
OI is sigma Z.
yes,
And OJ dagger is identity.
yes. So this is a 2 x 2 matrix,
This
the
is a
moment
true.
matrix.
So it
Yes,
is a trace of 1 1 10 1 1 sigma Z.
yes.
Now trace of 1 1 sigma Z would be -1 actually,
Mm-hmm.
because sigma Z has the two eigenvectors 0 and 1, and the minus eigenvector minus eigenvalue, so it has a two eigenvalue +1 and -1, and corresponding eigenvector of -1 is 1 1. So I'm taking that one as a row, so then it would be -1, right?
But so if you take OI, say the first entry will be rho Z,
Sigma Z.
sigma Z times sigma Z, or J diagonal.
No, no, OJ dagger I'm taking identity because it can be different.
No, no, no. But look, this is a matrix. No, the first one is 1, 1. The
Okay,
first entry is 1, 1. So the same object appears here in the first place. So that becomes 1. Trace
okay.
of
Yeah,
row
yeah,
1.
I got your point. So maybe
Yeah.
it is like the Krauss's type of things, EK dagger, EK, so
No,
that
no, no. I
you are
know the
saying,
proof. I'm telling you, I know the proof, and I'm also telling you the proof that for any linear operators, these are
okay,
always positive semi-definite, which is, look, the simplest way to state the proof, and I will go into details, and you can look up just the gram matrix uh, um, so consider a pure state. Then such a matrix forms a gram matrix, and gram matrix must be positive because of some physical reason. But I will also show you the proof later. But at the moment, you must trust me. Okay.
okay, yeah,
So,
sure, sure, sure.
so, but we will play. We will play. Oh,
Sure.
okay, let us not trust anything, but we will see. Such a matrix is always positive semi-definite
Sure,
matrix.
sure.
I will change it a little bit at the end if we get there, but let us go ahead.
I think Anand had some questions. I think Anand, please, you can ask. No. Okay, okay, please, Anubhav, please.
Okay. Okay. So similar to yours, but slightly different. Here are measurement operators. So instead, so you have identity in the first place, then say first eigenvector of sigma z and something like that. But we are only looking at symbols at the moment because we want to code with this. So there is identity. Then the first measurement first the operator corresponding to the first outcome of the first measurement of Alice, and um, then the second measurement of Alice, the first outcome, and then similarly Bob's first outcome corresponding to first measurement and first outcome corresponding to the second measurement for the CSSH scenario. Okay, we will take O1 to be this, and what will be O2? So NP hierarchy is a hierarchy. Hierarchy must have a number. Like corporate hierarchies has paychecks or whatever, but this hierarchy has a number, and this is called the level. The level of the hierarchy direct is defined was defined in the original article to be the length of the maximum length of the string of measurement operators in your operator list. Okay. So the second level of the hierarchy will be your all the strings of length 1 which were included in O1 union with all strings of length 2. So those include A terms, AB terms, and BB terms. Now, using this, the problem becomes an SDP. Membership problem becomes an SDP. I'll show you how. So we consider a moment matrix in the simplest CSSA scenario. Then we know that all terms of the moment matrix, because it's positive semi-definite, it's Hermitian, the other terms are determined, that all terms in the moment matrix, except for these two, have a physical meaning in Bell experiments. They correspond to probabilities. And they correspond to only the probabilities of the CG notation because we have considered only linearly independent set of operators. a second measurement of Alice and a second measurement outcome of Alice for both settings and Bob for both settings can be created out of these operators by subtracting them from identity. Um, Barring these two terms, all other terms are probabilities and they must be positive. If this moment matrix has to satisfy, it has to be a quantum moment matrix or even a valid moment matrix. But these two terms, they have no constraints. They could be complex. I think it's sufficient to take them to be real. And the computer would look at, would search over these terms essentially to find a positive semi-definite moment matrix. Okay, and there are some constraints here. The top row corresponds to the marginal, and so does the diagonal. So just these constraints, and um, and if we run this program with an objective function of maximizing the CSSH inequality, we get the Sirelson's bound. So so there are three steps to relaxing the Sirelson's problem or finding the maximum violation of the inequality. First, we give away the tensor product structure for commutation relations. So if there is cointensor product structure, then we have commutation relation. Also, in finite dimensional Hilbert spaces, if we have commutation relations, then we have tensor products Hilbert structure, Hilbert space structure. But it is not so in infinite dimensions. So there is um, less than equal to here. And then finally, we relax it via the moment matrix technique that I showed you, where now the probabilities are replaced by entries of the moment matrix such that the objective function is linear on the entries of moment matrix, and the moment matrix is supposed to be positive semi-definite. And then there are a bunch of linear constraints, such as the first entry always equals to 1 in our formulation of um, the moment matrix, and and equalities implied by commutation relations and orthogonality of projective operators, um, and cyclicity of trace. That's it. But those are some linear constraints. So this is the main idea of getting upper bounds from the NPA hierarchy. Now, one can clearly see that if you increase now one can, it, it can be seen easily that if you look for moment matrix of a particular level, that set bounds the quantum set always. It is also known that if you increase the level, you get a tighter bound on the uh, quantum set. And you can intuit this by considering the fact that now you have a larger moment matrix and you're demanding its positive semi-definiteness with more linear constraints. Then this is a more constrained problem, so it will give tighter bounds on violation of or maximum violation of Bell inequality. And so the so you get tighter and tighter bounds on maximum violation of Bell inequality when you go up the hierarchy, and tighter relaxations of the quantum set. And also in the NPA paper, the biggest thing that they show is that this hierarchy converges to the quantum set. So as L or the level tends to infinity, you recover the quantum set. So in some way, this is a complete method. Only the programs become harder and harder to run from just
No, your slide is not visible right now.
okay.
Now
I'm
it's
not
okay. Now it's okay.
okay. Sorry.
Now it's
Uh,
gone.
why is it happening?
Now it's okay.
I'm just looking. Just 1 second. It's okay now. Uh-huh.
Yes, okay.
Okay. So this slide was visible already or not?
Yes, yes. Yeah, it was already visible. Now
Okay.
this one is not visible.
Okay. So
Here it is.
I will show you quickly that this up to computational precision, this is the easiest way one can recover this very special number of 2 root 2, or in our case, this would be about, look, in the CG notation, this would be 0.707 minus 0.5, which is 0.0207. Okay, so I will quickly show you this thing. Just one second. Ah, okay. So just like in uh, just like in the slide now, just one second. Then something else.
So Anubhav,
Yeah.
so sorry, before you progress, so you have two methods, like just I want to validate something to see
Yes.
that I understood the part well.
Yes.
So you have two methods. One is the seesaw,
Yes.
right? And another is the using the hierarchy where you replace the tensor product with the commutation and then with the process matrix.
Yes. I will. I
Sorry,
will.
not process matrix, then with the, the gram matrix, the elements of
Well,
the gram.
moment matrix. We call it the moment matrix.
Yeah, the
But
moment value.
but it is on the screen at the moment. If you both of the methods I will show on the screen. But please ask your question.
Okay, so now my question is that, can we like compare like these two methods will compare between these two methods to some.
One is to get lower bounds on the maximal violation of Bell inequalities dependent on dimension, and the other one is more cryptographically interesting to get upper bounds which are dimension independent. The moment matrix based method is independent of the Hilbert space dimension, and so we can use it to optimize over what eavesdropper and device independent cryptography could possibly have. And one is more for just finding out best strategies.
With the seesaw.
With the seesaw, yeah. So
Okay.
I will just because of lack of time, I will just explain one of them, which is the main focus of today, the NPA hierarchy. The seesaw I will just glaze over. But okay, look, as I showed on the slide, the moment matrix will be 5 cross 5. Okay, and what constraints do I have is the first element is 1, and the moment matrix must be positive semi-definite. The other constraints only are the ones that the top row is equal to the diagonal. Okay, then I just map the probabilities where I place the probabilities in the moment matrix. I just map it here. Okay, which includes only the probability, only the marginal probability. So this is the CG notation. Marginal probabilities in the top row, and just the global probabilities. So the way to look at it is way to quickly check if it is correct. These are all probabilities of 0 0 outcomes in all possible conditionings in the CSSH scenario. And if we and our objective function is the is the CH inequality basically, and we just solve it using some common but very useful semi-definite programming uh, solver, and you can see that uh, the program returns uh, the optimal value, and you can see it's optimal up to computational precision, so upper bound. And this is exactly the quantum bound. And I will just go over seesaw. The seesaw had 3 steps. So one is over the states, the other is over Alice's measurement, and the third one is over bomb measurement. And it returns the same. It returns the same value. Just one second. All right. Okay. So this was also covered in the last section, so I will go quickly. In the simplest scenario, we have Jordan's lemma. So we know that the NPA hierarchy of some finite level should be enough to characterize the quantum set. What about but what about the level of the NP hierarchy? For a long time, it was believed that level 1, level 2, or almost quantum correlations, which are 1 plus AB between 1 and 2, are enough for the CSSH scenario. They're easy to write out and solve analytically as well. However, in our recent work, we consider Bell inequalities of the tilted Bell inequalities of the form, which includes your CSSH inequality and some tilting parameters, alpha and beta. And we find out using reduction to qubits, which is only applicable in binary input-output Bell scenarios, that we found a way of finding the maximum violation of Bell inequalities here, independently of NPA hierarchy or the SOS decomposition method. But here, the nice thing that we found, it's in the simplest scenario, the 2-2-2-2 scenario, is that then alpha and beta tend towards a critical region, which is given by alpha plus beta is less than equal to 2. As it moves there, we require higher and higher levels of the NPA hierarchy to get the tight bound. So we got the tight bound from self-testing, and then we use NPA hierarchy and saw at what level that we got the bound. We could check all the way up to level 10 using an arbitrary precision solver, that even level 10 of the NPA hierarchy was not enough. That means you are already including constraints corresponding to all strings of length 10 of the measurement operators. And this phenomena has seems to be linked to the measurement incompatibility of the self-tested measurement operators, okay, which we find in the paper. The way to see this is look at this graph here. When say beta is equals to 0, we know that level 1 plus AB is enough. And for 1 plus AB, Alice's optimal cosine on the right side. In the right side, we have Alice's optimal cosine versus the tilting parameter for different values of beta. So Alice's optimal cosine is a measure of incompatibility. So if it is 0, if the cosine is 0, then the measurements are maximally incompatible. And if the cosine is 1, they are completely compatible. And we can relate these two phenomena, and we find that the incompatibility, we can find regions of incompatibility where this phenomena occurs. It seems to be related to incompatibility, and this is an open question to address this. But okay, so this was about the tool with a little bit of demonstration, and I can go back to that again. So now I will just go over some of my applications. Yeah.
Anubhav, even in this simplest scenario,
yes,
for non-maximally entangled states, I mean, can we certainly say that, okay, there always exists a level of NPA for which actually it would saturate?
Yes, but we don't know the level.
Yeah, but can we just say, okay, there would exist some finite number of...
No, not finite, but yes, finite level. There should be a finite level, yes.
And how we are getting sure of it, that with some finite level it would be?
Okay, so I will tell you the basic idea. In the original paper, it is also mentioned there. So if you use this scheme of NPA hierarchy, and if you increase the size of the moment matrix, the optimal quantum setup appears in the moment matrix, and you can detect it if the moment matrix going from one level to the other has a rank loop. Okay, because of Jordan's lemma, we have a two-dimensional realization for the whole of CSSH scenario and all generalizations of it, like the GHZ scenario and so on and so forth. For that, we know that level 3 or level 4 should be enough to get such a rank loop for any quantum point. So we have this we have this level 4 for checking membership for the simplest scenario already. We do not know whether for maximum violation there will exist a finite level or not, but we know that NPA hierarchy will converge to the quantum set here, because there is no problem of because there is no problem of commutation relation and
Kanjinalda, can you mute yourself, please? I think this noise is coming from your end. Yes. Thank you.
so look here, there is no problem like I3322. We know that finite dimensional quantum systems are enough because of Jordan's lemma, which is the thing that we use to get the exact quantum value without NPA hierarchy. Okay, so here qubits are enough. And
so from here, can I make this kind of bullshit comment? I don't know.
no, please go
So
ahead.
suppose,
There's no
for example, I mean, if I say, okay, or if I want to look into the two input, two output correlations, and can I make this comment that, okay, the finite dimensions, using finite dimensional quantum Hilbert space, all two input output correlations, the set of all two input output correlations, and infinite dimensions, using infinite dimensional Hilbert space, the set of all two input two output correlations would be equal?
yes, always, yes.
Okay,
Because
good.
of this, it's because of this extremely interesting thing called Jordan's lemma here, which is basically a proof that you can divide such Hilbert spaces always into direct sum of two-dimensional Hilbert spaces, and then basically reduce to one of those pair of those two-dimensional Hilbert. So,
Great. Because
so
from this reason, we are getting confident that there would be some finite level of NP hierarchy, so that it would be same. Yeah.
yes, but it is not numerically solvable. So on the right side of this figure, I attach plots that I use a very high, or we used a very high precision solver to get. And already running level 10 in the simplest scenario is very computationally hard, especially if you want the values to be high precision. So um, it's about numerical characterization also. So we know that even the simplest scenario, nature's boundary is very difficult to characterize, or quantum boundary, very difficult to characterize. So um,
Thanks.
computationally hard. Okay, so and it seems to be related to the incompatibility of the self-testing operators. Okay. So now this is more on the theory side of and more news and theory about the tool. But what can the tool do for me? Device independent information processing is meant for is a cryptographic scheme, or uh, the main source of power here in device independent information processing comes from violation of Bell inequality. So if you have a correlation that is non-local, which means it's no signaling but it's outside the local set, then you know that it must have some randomness on offer. This is just because you can write the local causal condition as no signaling plus determinism, and if no signaling is still preserved, then you have randomness. We want to quantify this randomness, and a good and a generic measure that people have used is not the best measure, but it's a generically applicable and easily solvable measure, is that of min entropy. Now min entropy is generally defined to be negative log of your guessing probability. Okay, and the guessing probability optimization looks like this. So you want to maximize um, some linear combinations of some underlying probability distributions, or uh, um, which which can add up to your observed probability distribution. Okay, and the underlying probability distributions must be quantum. Okay, so you're basically trying to maximize the guessing of Alice and Bob's outcome, and your constraint is that you observe probability distribution p without any subscript. And what could you possibly do to maximize this information is that you can have decomposition of your observed probability distribution uh, uh, into other smaller into distributions that must, and those distributions just need to be quantum. Okay, the dual of this problem can be formulated in here it is searching over probability distributions PAB that becomes quantum. The dual search is over a real vector f and minimize the quantity f dot p. And this f must upper bound your probabilities PAB xy for all AB outcomes, and this P must belong to the quantum set. So this is the primer, and this is the dual. And this is one of the dualities that we found. So such a program, um, or the primal program, can easily be, both of these programs can be relaxed to NPA hierarchy, and this would uh, just be formalized by replacing Q by QL, and then you can lower bound guessing probability, and which means you can lower bound, yes, you can lower bound guessing probability, and also lower bound randomness. Yes. uh, Given your probability distribution, which is non-local. Okay, so you have your certificate, and the maximization tells you the amount of uh, randomness. Okay, but one then asks the most important question here is, what are the best strategies for getting maximum randomness? So this question is already dealing with the finite dimensional Hilbert space. So this article I found here on the top right uses the primal dual relation to formulate an algorithm, which is here, to find out the best strategies. And this program uses the previous program for guessing probability as a subroutine. So um, it's basically something like a method of first you get the um, first you find, you call the function and find the best find the guessing maximum guessing probability, and use the solution. The dual program returns you an optimal f, and use the solution to compute the minimum of guessing probability with the measurements, and then supply it back in the next loop, and this thing will then converge to a point. Here we are finding the minimum of the guess, minimum of this function g1, which includes f from our previous optimization step, which was finding the maximum of the guessing probability, and times probability distribution that comes from pi1. Okay, and we are optimizing on the quantum setup, which is defined by pi1. So in one step we are checking the guessing probability, other step we are optimizing the quantum setup, and they use this to find the best strategies for maximum randomness in the CSSH scenario. So all SDPs, and also a very good application of primal duality. The other key application of device independent information processing and of Bell inequality, Bell inequality violations and study of non-locality is device independent quantum key distribution. Okay, here we model our observed probability distribution as coming from a quantum realization shared between three registers. So some register of Alice QA, some register of Bob QB, and some arbitrary register of Q of an all powerful quantum eavesdropper E. And the measurement operators, and the probability distribution comes from some measurement operators given by the M here, given by M's here, and N for Bob there, times identity. So Alice and Bob see this distribution, and one more important thing to keep in mind for QKD is the post measurement state. The post measurement state of Eve's quantum register after the measurement, after Alice has performed X measurement and observed A outcome, and Bob has performed Y measurement and B outcome, then the rate of a DI protocol is given increment over strategies of the eavesdropper. The von Neumann entropy of the post measure von Neumann entropy of the post measurement state of the eavesdropper, um, um, uh, encoding how much information the eavesdropper has. This is the conditional von Neumann entropy of the conditional state of the quantum register, conditioned on Alice has measured X and observed A. Okay, so it encodes. This is not guessing probability. This is not related to min entropy directly. But min entropy, but von Neumann entropy is always larger than min entropy. So we can solve the min entropy maximization problem like in the previous thing to lower bound von Neumann entropy. And in this article here, they provide a generalization of this for I will come to that. But basically here in the program here, we will be optimizing on POBM elements of each dropper that guess the value of A. Okay, so this is such a program. The last sentence just says that some Bell inequality is violated. The other things are conditions related to measurement operator and to this additional POBM, which is applying on Eve's Hilbert or Eve's register. And this can be relaxed by essentially including commutation relations. Now, in this article above, in this article by Peter Brown and the Fubsy brothers, they give NPA relaxation that is better than min entropy estimation for conditional von Neumann entropy. It's here. It's too technical to talk about, but it can essentially be understood in the same way as the min entropy optimization, just replacing Z by this operator here. Okay, so it's very easy to understand, and this is contained in the basically in on his GitHub here. And this is much more helpful. The user guide is much more helpful than the Nature article, just for interested people. Just 1 second. Okay, so essentially the biggest application of Bell non-locality, which is DIQKD, can essentially be estimated or relaxed to a NPO or NPA optimization problem. And finally, these optimizations are also foundationally relevant. So I don't know if many people are aware of generalized non-contextuality, but this is also a prominent notion proposed by Robert Specken. And here we would like here the experimental setup is different from Bell scenario. It's a prepare and measure setup. Then Alice has some preparations labeled by X. Bob has some measurement Y, and and obtains an outcome K. And the preparations could be of any theory. They just are denoted by the alphabet P, and which is indexed on the input X. Okay. So preparation contextuality scenarios are prepare and measure experiments with some additional conditions. These conditions are still independent on the Hilbert space dimension, and these are like this. The effective sum of the first and second preparation should be equal to the third and fourth, and so on and so forth. Okay, I think I am running out of time, so let me go over this very quickly. So, and here, in such experiments, we are interested in again bounding the set of quantum correlations. which again turns out to be convex. Again, I recall that there is no Hilbert space dimension. And in general, the operational equivalences, which is the additional constraint, they could be written in this form. So basically, it's equivalence of several linear combinations of the states. Okay, and here I'm just taking convex combinations, but it will be generalized to linear combinations as well. And similarly, there are operational equivalences of measurement, which are linear combinations of the measurement operators, different linear combinations becoming one effective linear thing. The other way to read it is that there are a bunch of states with several different decompositions. And similarly, there are a bunch of measurement effects with several different decompositions. So such a thing or such a system of a prepare and measure scenario with such condition forms a contextuality scenario. So basically, a contextuality scenario is a tuple of what are your prepare and measure settings and operational equivalences of preparations and measurements. Okay. So again, this is a difficult problem because of the Hilbert space dimension, and there is no efficient characterization. So we wanna give an hierarchy in the sense we wanted to give an hierarchy in the sense like NPA hierarchy, but for generalized non-contextuality uh, scenarios. The main challenges were that that we cannot consider pure states, nor can we consider projective measurement. These gave sharpness to the NPA hierarchy and made it converge very fast. But without these, the NPA hierarchy fails to converge. Okay, so these were the two challenges, and the way we address this is the way we notice that we can consider a bunch of movement matrix, each hinged on a preparation. So preparations, they translate to labels of movement matrix, and the measurement operators then can be inside such movement matrices. Then the operational equivalence conditions being linear on the states or the preparations, they directly translate to operational equivalences of moment matrices. So direct to equivalence conditions of on the moment matrices. So this essentially from density operators to a moment matrix, because of this hinging, this essentially resolves our first problem. For the second problem, we consider something very interesting. That is any positive semi-definite operators which is bounded by identity. It might not, it must not be bound. It can, no, it must be bounded by identity, has this decomposition. So identity over 2 plus unitary plus unitary dagger over 4. So our challenge was that we don't have projective measurements. So if we have projective measurements, then we have this diagonal thing always equal to in the Q1 level to the top row, and this helps the hierarchy to converge. But if we do not have that, if we must consider POBs, then the hierarchy stops to converge. So what we used is this lemma that any positive semi-definite operator can be written as identity over 2 plus some unitary plus its dagger. So you have e to the power I theta and then e to the power minus I theta. So you get I think 2 cos theta plus over 4, and you have 0.5 coming from identity, and this can create any positive number between 0 and 1. So we use this lemma to have a moment matrix now hinged on preparations, but having entries as the unitary operators, and so that the diagonal entries are now exactly 1 always. So that those becomes a constraint, and the hierarchy starts converging very well. And we designed such an hierarchy, and then we can report. We reported on several on tight bounds up to numerical precision on several Bell inequalities, and also proofs of many interesting things in contextuality scenario that are foundationally relevant. And yeah, sorry, this is not, yeah. And we also found an application. So which is basically SDI-QKD based on operational equivalence, and we use the 3-to-1 parity oblivious rack in it, and should and got the function of key rate for Alice um, as a function of Bob's success probability in the 3-to-1 rack. We made this is a just show possibility. So it has a lot of assumptions. Like all the rounds are IID. There is free will assumption and no quantum memory for each of them and preparation equivalent. So this is a very restricted case, but just to showcase the hierarchy, we found these key rates as well. So this is it. Hopefully I have it was very small time. Hopefully, I have given you some idea of how the hierarchies work, and in the last section, convinced you of their importance, at least practical significance as well as foundational significance. So, thank you, and I am happy to take questions here, or you can write to me later, whichever way.
Oh, thank you, Anubhav.
Thank
So
you.
now we can take few questions. Please go ahead.
So I will first. Can I take your question first?
Yeah, sure.
Okay, so I think it's maybe it's in this article. Otherwise, I will send it to Horizon and Valero. A very, he calls it a very specific tool here. Yeah. You can see the proof here. It's a one-line proof. So F2M are any operator. So there is no in the orthogonal matrix N, whose entry is this is the moment matrix, is non-negative. And the way they prove it, they consider for any real vector. If how to prove positive semi-definiteness, this number should be positive. And so if I take any real vector V, we still have these combinations, and we know that because both rho and any operator of the form C dagger C are positive. So if you take any linear operator here, this is positive, which is why the moment matrix is always positive for any linear operators. And I also showed you the example with changing the measurement operators with unitaries in the contextual scenario.
Okay, thank you. What's the title of this? Okay, can I send it to proof?
Okay, yeah.
That would be great. We can take it as a reference.
All right.
It would be helpful. Okay. So I have one question. I have another question, but
yes, please go ahead. Please tell me.
Yeah. So what I'm saying, in the prepare and measure scenario, so suppose when we are talking about the correlation space, that was PAV given XY, right?
Yeah, yes.
But now in the preparation and measure scenario, there are also some PB given XY, some correlation space and some, then again, it could be some convex set.
Yes,
right?
yes. Especially if you if you allow for shared randomness for classifying.
Yes.
Then you have convexity for all sets.
Then we have a convex set. Yes. Now what I'm asking, so here, I mean, if here also, I mean, I can take quantum systems as my communication means or communication. I can use quantum system as well as I can use GPT or whatever. These things, right?
Yes.
So, so if someone wants to do the NP hierarchy, then they don't consider the dimension. I mean, here, yes, here you have to obviously consider a dimension dependency for the channel, right? I mean, what kind of? Oh no. Okay.
This is only thing, or the only constraint here. It is only constraint is of are of these forms. Some preparation is equivalent to some other preparation, but this is only for mixed preparation. So something like this. See, this is a simple example. So you have 6 preparations. They could be arbitrary GPT preparation. They must only agree with these equivalence conditions.
Okay, but if suppose I'm asking you a little bit general questions, mean the simulation of P K given X Y. Suppose X has some fixed coordinate, Y has some fixed coordinate, and K has some fixed coordinate. And now we want to simulate by a qubit or by a gbit or whatever it is. Now here I think the dimensions of the distinguishability dimensions has to be same. I mean the channel they are using, they has to be either one bit. I mean it can carry 2 distinguishable things or 3 distinguishable things. They have to be same, right? Otherwise it would be trivial.
Oh yes. You're saying that. Um, mm, uh,
I mean I can compare
we
qubit
only
and cbit only.
if no, if you take the here, the reason is not the amount of information. Here's the reason. Here the constraint is about the type of communication. So or what must be kept private in the communication. It does not matter if your amount of communication is too large or too low. The problem remains non-trivial up till these new constraints are fulfilled. Forget this, but consider one side of the Bell experiment, say the CSSH Bell experiment, okay? On just Bob's side. So there are 4 preparations, which are given by row A given X. So 0, 1, 1, 0, okay? These 4 preparations must satisfy no signaling constraint, which is an operational equivalence condition of this form. So one side of the CSSH in CSS scenario forms a preparation contextuality experiment. Now, because there is no Hilbert space dimension on the CSSH scenario, either in the quantum space or in the local set, there is no corresponding Hilbert space dimension on um, um, on the Hilbert space of the prepare and measure system. And specifically, when you look at the same correspondence for I3322, then you can get the statement that no finite dimension is enough because
No,
there is one-to-one correspondence.
no, that is okay, but I'm asking a little bit different questions. Suppose you have a coordinate of x, y, and k fixed. Now, what I'm saying, suppose I'm sending a qubit and to try to simulate. So because okay, I'm taking a qubit and as well as shared randomness. As much shared randomness is required, I will take that. So it would be a convex set. But my question is, still this convex set would also be the same type of problem would be there, like a boundary should not be defined. It would be same problem, right?
Yes, yes, similar problems. Yes, and
Similar
the
problem. Then also
yeah,
in the NP hierarchy also here also it might not the SDP and NP hierarchy, they for them also it would not saturate, this kind of things would still occur, right?
yes,
Okay.
yes, it is the same thing. Because yes, exactly, exactly the same problems, and I think you're right, but all right.
Yeah, that's the
Actually,
thing.
mhm. Yeah, but again, like NP hierarchy, it's a handy tool, and it already lets us get the exact quantum violation for a lot of uh, generalized non-contextuality inequalities.
Yes.
And also dimension independent. So that has some value to cryptography as we explore.
Obviously, there is a lots of other applications which you have some of them you have explained very nicely.
Yes. Okay.
Thank you.
I
Thank
hope
you.
it
And
was. Yes, I hope
yeah,
it
it
was. Yeah.
was very nice because this was the first time I was listening from someone who is expert in this field. So very nice to hear from you. Maybe I'll, if I get any confusions, I will directly ask to you. That would be.
No, come on. You are with the origin. You're at the
Oh,
origin of MBA.
that's true
So,
then.
so you have
Yeah.
to tell me a
No,
lot of my questions from that place because that is a great place to be in, and because the your Vetoniacin and NPA has. Thank you, Mir, for this, and let
thank
us
you.
continue to discuss. That's all. I
Yeah,
hope.
yes, sure. And so anyone has any other questions? Maybe we can take it. Okay, I think probably no one has any other questions.
Thank you.
So thank you, Anubhav, once again.
Thank you.
Um,
See you.
yeah. Bye.